Hi, I'm GUO CHENG GUANG, 15 years old. In this lesson, we will be taking a look at physical chemistry. And in this part of physical chemistry, we have the Maxwell-Boltzmann distribution. Alright, so right now, we have this example that we need to prove. But in this example, there are some of the things we will need to take a look at first. So, in order to prove that PV is equal to 1 over 3 nm, the root mean square velocity squared, and U is equal to kinetic energy plus N with this sign and epsilon inside, and it's equal to 3 over 2 nRT for ideal gas. So firstly, you might not know what each of these letters mean. And in this lesson, we will be taking a look at the first half, alright? So the second half, we will be leaving it for later lessons. So, the first half, PV is equal to 1 over 3 nm root mean square speed squared. So, PV, where do you normally see P and V occurring together? Well, that's right, your ideal gas law or your state equation. So, generally you'll see PV equals nRT, but now you have a PV equals something else. So 1 over 3, N would be a number of particles within the container you have. M would be the mass, since each of them you would be using the same mass, as you wouldn't really want, like, in your container, particles with varying masses, alright? And of course a root mean square speed. So we did have a few different types of speeds, and you can go back to previous lessons to check out the 3 different types of speeds, alright? So root mean square speed is one of them. Alright, so you have to be aware that that is what you need. And what is your condition? For ideal gas. Now what is so special about ideal gas? Yeah, of course you have PV equals nRT, which is your ideal gas law, but what is so special about this ideal gas? So of course you would have a mass, but they do not have sizes, alright? So the size just approaches, or you basically take them at 0, alright? So they do have a mass, they don't have a size, and other than collision, particle and particle, they do not have any other interactions, alright? So what kind of interactions am I talking about? If you have learned about intermolecular forces, you have, like, for example, van der Waals, or like hydrogen bonding, whatever you have, London dispersion force, those you would not have the interactions between them, alright? So all they do is collide into each other and bounce off. There would not be any chemical reactions between them either. So all the interaction they have between them are collisions. And what type of collisions? Those will be elastic collisions. So there will be a conservation in kinetic energy and a conservation in momentum, alright? And this of course also applies to the particle and the wall. They would also have an elastic collision, alright? So those are some of the main things you have in your ideal gas, for your ideal gas. And when you take a look at your ideal gas law, which is PV equals nRT, then N, what you would realize is N, for a container, it has to be completely sealed off. So there won't be any leaking or addition of gas and all, okay? So those will be the few things we have to take note of when you have ideal gas and ideal gas law. Alright, so now that we have set the stage for what we have, now how do you think we can show that PV is equal to 1 over 3 nm root mean square speed squared? So where are we going to start? How about let's start with a particle within the container that you have. What's so special about this particle? So let's say this particle, it collides with the wall, and this wall is perpendicular to the x-axis, alright? So in order to collide, this particle must have a speed in the direction of your x-axis, okay? Alright, so it collides into a wall, of course it bounces off with the same speed, of course different directions though. So what would be so special about that again? Now, what you can say for that is, well, how about let's take a look at a change in momentum for this particle along your x-axis, alright? So, how are you going to calculate this change in momentum? Now, momentum, of course, you would have your m multiplied by your speed, or mv in short. So mv, m, for the mass of this particle, we will still take it as m. So v, what would the v be? Now the v, since you're moving along the x-axis in order to collide with the wall, that means you would be using vx, alright? But vx, this happens if it is just mv, then it collides in the wall and stops. But since it bounces back with the same speed, you would multiply this by 2. Or you can also think of it as one positive and one negative. Well, positive minus a negative, you basically get twice of the original. Alright, so this is your change in momentum. This is along the x-axis. We aren't really talking about the y-axis or the z-axis, alright? So, what else do you think we can find from here? So, what happens if we want to find a force from this? So, why exactly do we want to find a force? Since PV, P is your pressure, and to calculate your pressure, you want force divided by the area that is acting on, okay? So that means we want to find the force. Now in order to find this force, now let's just say we have Fx. So what will Fx be? So Fx, you would have your change in momentum divided by change in time. So this will give us your force. Now, your change in momentum is what we have found earlier on, which is 2mvx, while your change in time. Now, how do you think you can find this time? Since from primary school, you would already have learned your time, distance, and speed relationships, right? So this time, you have traveled, so in the x direction, from the particle moving towards the wall, let's say the distance between them is x. So it has traveled to x. Well, you have to divide it by the speed in order to get the time that you would have, alright? So 2x over vx. Now, a simple calculation here will give you mvx squared over x. So this will be your force along the x direction for one particle, alright? So this is for one particle, the force for one particle. How about the pressure for one particle? So if you have your pressure, that means it is your force over the area of the surface. So what you would have over here well, that would be, so x. Now let's say we have x as your entire length of a container, for example a cubical container, alright? So x in this case would be, since it is over the area, that means you would have x squared multiplied onto a denominator for this part. So this is what you will get for the pressure in the x direction, alright? So this is just for one particle, beware. But since normally you would have like a lot of particles inside, that means we would have different speeds for each of the particles. And that means we would have to use something else to find them, isn't it? Now how about let's find the entirety of whatever you have. So this time it is for all the particles within the container. So m, we will just take them all to be the same, and this will still be the same, but let's just say we have Vx, let's say 1 squared plus Vx2 squared plus Vx3 squared, and until Vx, let's say we have capital N number of particles, alright? So this is what we see if we have n number of particles within this container that you have. So we can just write this into a sigma notation, and x cubed, we can change that into your volume of your container, which you'll see as V. So sigma from, let's just say this I, from 1 to n, and you'll have Vxi squared. Alright, so what will be so special about this? Now we can technically use this to find it in terms of a mean, right? You might be wondering again, why do you need to change that into a mean? But you'll see later on. So let's say you change this into a mean, which you'll see as Vx squared with a bar. So this is just your normal arithmetic mean. But since this here will be divided by your total number of numbers, as what you will call it, that means you have to multiply it again by an n, alright? So what else can you have for this part? Beware the difference between two V's, one is the volume and one is your speed, alright? So now in this case, what you would realize is Vx, this is just in an x direction, but you want in all three directions, x, y, and z. Now how are you going to calculate for x, y, and z? Well, that is actually pretty simple, since if you can recall from the beginning of this series, we did say your entire space would be isotropic and something else, right? And that something else would be whatever you have in the x direction will not affect what you have in the y direction or the z direction. So x direction, y direction, and z direction, they're all independent of each other, which means this here would actually be the same for x, y, and z coordinates each respectively. And what would you have to do? Since they're all the same, you can just add them up together. So, well, if you add them up together, wouldn't you have 3 times of that? If you have 3 times of it, you just divide it by a 3, isn't it? So you will see V square average, alright? But what else can we do from here? Now, you have a square, you have your average. Now that already makes up the square and the mean part of, what do you need here? The root mean square. So now you just have to square root this, right? Which means you would have to square it again. Or you could already move the v to the other side. That gives you, so you will be seeing PV, which is equal to 1 over 3, and then M and M. So this is actually V root mean square squared, right? So if you can see that. Alright, so this is pretty much what you would have for the first half. Alright, now let's say what we just had in a nutshell. So you started from your difference in momentum. So difference in momentum, you have a value since you have an elastic collision. And using that value from your change in momentum, you can find the force in the x direction. So this force, let's say you have this plane over here. Alright, and you hit it. So it hits it. Let's just say this in the capital X direction. So whatever you see is in small x, alright? So your particle would also hit it at small x distance away, alright? So that's pretty much how it is like. So from that, you can find your force, and with the force, you can find pressure, since pressure is just force divided by the area, alright? So, well, each of them would be x, so that should be clearer to find the area you have, alright? So, then this pressure, the first pressure, Px here, is your pressure for one particle only. So I'm going to change that a little bit just to make it a big difference from the other Px that we're going to see. Whereas this Px here is your pressure for every other particle, or not other, but every particle within this container of yours, alright? So with this, at last, you do a little calculation, and by the means of an isotropic space, the value in the x direction, the y direction, and the z direction are all the same, alright? So that means you can pretty much just remove an x here and say, well, this is the pressure that you're going to have, alright? So now one difference is the three different p's, one being momentum, one being your pressure for a single particle, and one being your pressure for all the particles within a container. Well, another difference that you have to make would be the two v's. One is for speed or velocity, while the other is for your volume of this container you have, alright? So those are pretty much what we used in order to arrive at our final step, which is PV is equal to 103 nm root mean square speed squared. So what use do we exactly have for this? We will explain more in future lessons. So I hope for this lesson, you can understand everything so far. I'll be ending it here, and thank you for your watching.